Welcome to this episode of Stack Walk. I'm Tim. Today I'm with Andrew Richards, who I worked with for many years.
Yeah, about 10 probably, yeah.
Yeah, about 10 years. Some of you may know him from Defect Tools, among other things that you've done.
Yeah, Inside Show as well on Channel 9, and then talk to Build Conference and stuff a fair bit about debugging.
That's right, yeah.
Or the hardcore debugging series, yeah.
Yeah. So, Andrew, tell me a little bit about how your career at Microsoft.
Great Microsoft. I'm just entering nearly my 15th year. So first 5 years was as an escalation engineer in support. That's actually how I got the job at Microsoft. And then last 10 is dealing with you and in the Windows reliability team, specifically the bang analyze command, which is what we call scale analysis, and we'll go into that in detail. Prior to Microsoft, about 15 years worth, I worked for did newspapers. My very first job was NT31, writing printer drivers that ran the presses. So you can't get a bigger printer in the world than a printer driver for a press. And then I wrote the international wire service, the thing that transferred all the stories around the world. That was all serial modem based. That's how old I am. And then I worked for Ericsson and did a whole lot of stuff that is actually now, 20 years later, relevant, and they walked away from it. Very PABX based stuff and chatbot and stuff. And then the big thing I did for about 8 years was write a bank start to finish. We started from scratch and changed the mainframe system from old antiquated stuff to a Microsoft tech stack. And then there's a Google search mistype. Back then it was Google before Bing. I'm definitely a Bing person now. I did a typo. I typed 7660 rather than 7600. That led to a page on Microsoft.com. It said, if you're interested in this page, email someone. We're interested in talking to you. 2 hours later, I was on a phone call with someone from North Carolina. A week later, I was here interviewing. I learned assembler on the plane. That was a requirement for the job for the 24 hours from Australia. I learned assembler, never slept, had my interview, and a week later, I got a job offer and went from Australia to the other side of the planet with a mistaken Google search.
You hadn't told me that one before.
No.
So that's interesting. You mistyped the search and you ended up on a jobs page for Microsoft?
So I typed in, I was actually destined to go work for MI6 to help them develop spy laptops. This was Windows Vista.
Mm-hmm.
And the exam for the Microsoft exams is 7600. And I typed 7660 by accident. And that's the code for Windows internal exam. Which is basically the escalation engineer. And I looked at it and went, this is fantastic. This is exactly, and at the top they were hiring. I emailed in person and it all happened. That's why I had to learn assembler overnight. I hadn't known that before.
Did you end up working in North Carolina or was that Redmond?
I was destined to go there. It was for Active Directory, and then they didn't have international reload budget. And so Graham McIntyre, which you both well know, suggested that I come over to here because Exchange had budget, and Exchange and Active Directory are kind of the same. Gotcha. So I did Exchange for 2 years, and then I moved to Windows support. Actually, Graham has hired me 3 times. Then I moved to Windows support, like server and stuff like that. And I was working with EMC a lot and a lot of storage type stuff, a lot of hardware stuff. And then I moved to OEM support, so then I went all the way down to the firmware. So over that period, I went from Exchange being C++ to C#. Then I went into Windows, into drivers, then into firmware. And so I had this very broad experience. And along the way, it's also how I met Rusinovich and ended up writing ProcDump, or rewriting ProcDump, I should say. So that started that relationship. And then that rolled into Channel 9 because I was finding that I was trying to learn things and it wasn't out there yet. So I pitched the idea that we should learn things, and that turned into 202 episodes of content. And then eventually, Graham moved across to the reliability team and writing bang analyze, and he pulled me again for the 3rd time. And so now Graham owns Task Manager now. So traditionally he leaves and about a year later I get pulled. So I'm about 9 months away from joining the Task Manager team from history. So
you worked on a pretty broad range of things, which is very different from my career, where I've done, I interned on Windows Vista. I worked a little bit at IBM. But I worked primarily on the debugger team for most of my career, and I had a little short stint on hypervisor. And I wonder, I suspect there's, just from your experience of this being really broad, there's probably things that it's probably hard to pinpoint where you got some experience from, but you've had this broad range of experience that's feeding into, your intuitions about how to debug things or how to approach problems.
Yeah, you keep on hitting these walls.
Yeah.
And so you go, okay, I need to go down to the kernel now, and then the world has changed, and we can talk about this. The world's changed from crashes to hangs,
Yeah.
realistically. Things just don't crash much anymore. I mean, statistically, I'm talking about. And then it just gets lower and lower. Okay, where you've got to use my program running slow. It's stuck in the kernel. Okay, let's look at the kernel. We've got a kernel program stuck. Okay, it's stuck in the BIOS or stuck in an offload to some hardware device. It's one of those evolution things. People ask me a lot how to learn how to debug. It's an evolution. I mean, you need to practice it. It's like, how do I learn how to write? It's because you write every day.
Yeah.
Right. How do I learn how to code? It's because you code every day. And the reason why the escalation engineers are so good is they do it 40 hours a week.
Yeah.
And I think there's also a balance there between the next level down or next tier is support escalation engineer. And they're really good at the troubleshooting thing, like narrowing it down and saying, do I need a dump file or is this a process monitor situation or ETL or whatever, right? And so there's a lot of learnings. And I think everybody should go work in support. Like, it teaches you how to talk to customers. It teaches you how to pick up a phone, which in these Zoom days is so important to keep connected with people with the hybrid working. Troubleshooting skills, and actually that's why I ended up doing the Defrag Tools series. I got sick of repeating myself, so I said, go watch the video.
Yeah.
Education is really important. I think that's one of the key things, both educating yourself and growing, and then also giving back as well. That's the thing I've learned. And Jason Eppley, which you talked about, he's an absolute master at giving back, like producing content and growing others. Yeah, I mean, I know that you continually get asked about how to debug. Like when you're in the debugging team, it's like there's balances of merit of like, am I going to teach one person or am I going to step back and use that time to teach more people?
Yeah, and it's kind of interesting because at the same time, I'm like you. I like teaching people. I like showing people how to debug. I like teaching people these concepts, but like you're saying, right? There's no replacement for experience. You have to learn through doing, and of course there's a balance, right? Where sometimes you have to learn some concepts, but you don't really internalize it until you sort of put it into practice and you've used it a lot. And so if you're just watching a video that's like how to debug a crash dump, but you don't go and debug a crash dump, you're not going to really internalize it. You're not going to be able to apply it or have that intuition that's building of how do you actually go and debug these problems.
The very first question I ask in a job interview is, write hello world, don't look anything up. I don't care what language it is, but I want every import statement, every include statement, every bracket to be correct. If you can't write hello world from top of your head, you haven't actually learned it because you haven't tripped over the understanding of how the compiler builds things and stuff like that. And even in the debugger, you can, I think it's even harder because it's a lot more data vomited at you at screen, and understanding actually what's important. It gets a bit matrixy, I will admit.
Yeah.
You just see the numbers. I remember when I was in training, Nick Rosenfeld, shout out for you for teaching me this. We had an exchange up. An exchange in those days was like 1,000 threads. And so we just printed out every thread. And he just let it scroll on the screen. And back then, scrolling wasn't that fast. Right? And he goes, what's wrong? And there was 2 or 3 of us all learning at the same time. And I went, I know what's wrong. I picked up that one thread was really, really long.
Yeah.
Right? And it was it didn't matter what the text was. It was that shape, right? And I've learned that over the years that the shape of the text is really, really important.
It's really interesting because, I've talked about this in other videos, and I've also done a blog post around recognizing patterns. And then the post I did was about recognizing patterns in memory. And there's all these little aspects of pattern recognition, and sometimes it's recognizing that something's not right. You don't always necessarily even know why it's not right. But you look at something and you're like, that's not right, and then you dig into it, right? That's hard to teach.
Yeah, it is. It's an experience thing. The thing that I've learned through the reliability side is the difference between frameworks, or OS, frameworks, and code. And so the OS is things like, create file and all the things that are making threads and stuff like that. Frameworks is things like, Unity, Unreal Engine, CLR, all these other language things and all helpers. And then there's actual code that actually does something. And if you can quickly segment it into the OS is calling into this framework's finally calling into the app has a callback into this framework, you can reduce it down to something that's humanly understandable. I don't care really what it's doing. I just know that this is the general flow, and whether that's probabilistically heading towards a crash, or it's probably finishing work, or it's probably waiting. There's a command in the debugger extension I wrote, which is PDE, used to stand for proc dump extension, but it didn't actually have any proc dump left in it. So I renamed it to prototype debugger extension. And the idea is I prototype stuff in it, and if it's worthy, we move it into a shipped debugger extension. And there's a command called deep. And you just go bang deep 10. And it's basically, it shows you every stack that has at least 10 frames in hex. Sorry, I always talk hex. So at least 16 decimal frames. And 99% of the time, that's actually going to show you actually what's important, because everything else is just sitting there waiting. It's kind of the boundary of the worker threads just waiting to go. You'll get it will actually be 16 frames plus if it actually matters. And in Exchange is a really good example where I wrote it for. 1,000 threads. I don't want to look at 1,000 threads. Deep 10 brings it down to 5, right? And it makes it manageable.
So it's interesting that it within debugging Exchange and other things, of course, right? You're learning kind of what questions to ask too, right? Like the question you're answering there is, what threads have more than 16 frames? And
no, the question I'll ask is, who's actually doing something?
Who's actually doing something? That's true. You're asking a different question, but you're answering it by saying, show me all the threads.
That's the heuristic I'm using to get there. A very simplistic heuristic.
Yeah, I mean, so there's this element of like pattern matching. There's also this element of like, you have to know the right question to ask to get to the problem. And it's not always easy, I think, to sort of, you can give people some ideas of like, these are the types of questions you should ask in these types of situations. And then as long as you know how to answer those questions, you can get to the data where you're looking for the patterns, you're looking for, those problems.
And then the next problem you get to, which is my entire career doing Bang Allies, is how do you describe that situation? Now you've got there, okay, I chose this thread. Well, is it a crash? Is it a hang? Is it user mode? Is it kernel mode? So we have 4 major metrics that we track, and Windows 11 is the best of all OSs ever. Like basically every release we do is better than the last. And we have 4 main ones: user mode crash, user mode hang, so application crash, application hang. Then blue screens, which is kernel mode crash, and then kernel mode hang, which is when your box really jams up and you do things like hold down the power button and stuff. And we track all those 4, and we treat all 4 as separate projects. And then within them, we actually then do languages, so like C++, C#, Java, JavaScript, blah, 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 which I'm currently harassing you about. Rust is another big one that has turned up recently.
Yeah.
And then there's actually another pivot, which is the CPU. So then you're going to go 32-bit Intel, 64-bit Intel, 32-bit ARM, 64-bit ARM. And then recently, over the last probably 4 years, because of the target model and what it opened up, was non-traditional things. So GPU analysis. And if you think about like the Apple Vision Pro, it has an M2 and an R2 in it. R2 basically is a holographic chip, same as a HoloLens. HoloLens has 3 chips in it. So Apple's doing it by putting the CPU and the GPU in the M2, and they're putting this holographic one in the third one in the R2. So with HoloLens, there was a distinct CPU, GPU, and an HPU, holographic processing unit. And so they're not normal CPUs.
Yeah.
And so our matrix is getting wider and wider because what the debugger can.
Yeah, and just to explain a little bit what Andrew's talking about with the target model, for those of you that haven't, followed the, some of the things I've written, the evolution of the Windows debugger. So the target model was an evolution of the Windows debugger to enable support for new types of targets. Targets could be, a new crash dump format, or like Andrew's saying, things like an entirely new type of system architecture or new operating system. That was part of the evolution of the Windows debugger towards supporting Linux.
Yeah, it's a fantastic abstraction because it was designed not only to abstract the OS, but actually the idea of compute.
Yeah.
Right. Registers are now no longer confined to being CPU-centric ones. Right. You can project a GPU. You can project something weird. And then if you think in data centers, there's all these custom silicon chips that do storage and networking that actually aren't in the rack anymore. There's dedicated silicon that they're pressing. Microsoft, Google, everybody is making custom silicon because it's more power efficient to run this custom ASIC. And so, that's an emerging thing. And I know talking to people down in Silicon Valley, they're expecting that to be more and more prevalent because just from a power point of view, it's going to be more efficient to offload that Kentucky.
We hit limits on what you can do with like just keep making. And then when we did this for a long time, CPUs are just getting faster and more power efficient every single year. And I haven't looked at the curves, but I assume that's tapering off. We're not getting
the quantum limits hit at 2 nanoseconds.
Yeah, right.
And we're really close to what 5 now, I think it is. So we're not that far
We're
away
not far
from.
from the quantum limits, and so we're kind of slowing down there. So yeah, I mean that makes sense. We're going to get more and more specialized hardware, specialized CPUs,
Yeah.
and so yeah, new hardware means new debugging techniques and new types of debugging targets.
It is, and it blows your mind. Like you start going, oh, why is a shader blocked rather than why is a thread blocked, right? You're not
Right.
thinking about
Yeah.
a call stack anymore. Now you're thinking about vectors in a certain configuration that causes a loop.
Yeah.
MPUs is the next big one, without disclosing anything. But obviously MPUs are coming along and they're their own core and they're going to require their own dump file format. And that's the next thing I expect to work on a fair bit. It just needs to be, right? They're going to be MPUs that crash and hang, and they're no different to any other piece of silicon. They can always crash, they can always hang, they can always do, bad memory faults and have bit flips and all that type of stuff.
Yeah, so it's interesting you mentioned bit flips, and I know we want to talk a little bit about like what does it mean to debug things at scale.
Yeah.
That was something that I found incredibly interesting as I started to do things on the debugger team that were contributing to Watson, was that when you're debugging at scale, you start to see these stochastic, probabilistic things that you would never in a million years see, or very likely not see, if you were debugging things sort of by hand. And these are those sorts of things where you see bit flips. I literally remember where we'd be debugging something and we that could have been a cosmic ray. That bit is flipped.
We actually track that. We actually have reports that track two main things that we do is we correlate all the telemetry in the world, again, or people who understand it, of course, against power outages.
Yeah.
So we actually have code that scrapes the internet and finds all the local power agencies and gets their reports of their outage maps. And we work out whether that region was close to the region and someone who had an outage. It's like, why did the PC drop? Was it drop because they went, screw this, I'm pulling out the power? Or did it drop because of the local power authority? And the other thing we do is we look at the solar flare calendar.
Did you see correlations with solar flares and bit flips?
Yeah, it's not huge. I mean, bit flips it's about 1% of 1% of traffic that we see, right? But we only get, the rate of failure is very, very low. And so you're in a very percent of a percent situation to be in that. The main thing that changed is, I think it was like Windows 10 or maybe 8.1, they changed the way the page file works. So normally you get this 4K page, and then when we're out of RAM, you pick it up and you put it on the hard drive. And then when it's time someone asks for it, they pull it back into RAM. And so the disk, which at that point was very rotational, you would have a lot of magnetic mistakes. But to speed up the outright, they changed it to compress, and they actually use the Hibernate file format, or the zipping, or the compression format. And so they actually have to write less. So when they're writing out like a megabyte, for example, they only have to write out a couple hundred K, right? Faster I/O. But because of that, they have to checksum it, because compression includes checksumming. And so now when it comes in, we detect that the page is checksummed wrong, because what went out doesn't equal what came in.
Right.
And so all those bit flips are now not an issue, because now we have blue screen.
Yeah.
Because a single bit is enough to be,
at least for the memory that's paged out.
Yeah. Well, when it comes in, if it's bit flips, that's it. We blue screen, because that bit flip could result in a human life-threatening situation.
Right. Yeah. If you corrupt data in a way that you're not detecting. Sure. Yeah.
Yeah. Totally. And sure, you can have some financial mistake or whatever, but when it comes down to it, Microsoft looks at a lot of things and goes, could this cause a life event?
Yeah.
And a lot of the answer is true, and you're better getting out of that situation than. Much more emphatic than being lackadaisical about it.
Yeah.
And then RAM's got better. I mean, obviously RAM's got faster. People overclock all the time. If you look at the stats, lo and behold, guess what? All the bit flips come from overclockers. Surprise, surprise. But RAM's got better. It's just better quality. But there is a huge amount of it, right? I mean, it's terabytes and terabytes of bit flips.
So have you seen then the trends of sort of things that are suspected to be hardware issues declining over time?
Yes and no. There's more RAM, so there's more to go
more
wrong.
Opportunity. Yeah.
So the quality's up, but there's more chances of a mistake.
Yeah.
You also have to detect it, right? With the page file, you can detect it because we have a checksumming. But if it just happens while it's in RAM and never goes out to disk, you don't pick up the damage. And the thing is, it's a lot of data is benign. Once you've read it once, it doesn't really get read again. But it's not at a rate that we actually don't worry about it. It's good enough. We don't worry about it. We do, though.
You can see it statistically, but it's not something that you consider when you're like troubleshooting.
It's not worth my time. There's other things that I should work on. Well, also we can't fix it.
Right.
right?
Yeah.
Now in the data center, we understand this and we use ECC RAM, right? So most data centers use ECC RAM,
Hmm.
which corrects up to certain bits of flip, so it's recoverable. So
Yeah.
where it really matters, it's all, it's a risk benefit analysis.
Yeah, I'm wondering if at some point we're going to start seeing more ECC RAM being used in consumer machines. I know for a
It
long
has,
time,
yeah,
Intel would lock it behind their enterprise stuff.
they did.
AMD would allow you to use it as long as your motherboard supports it.
Yeah,
Um,
it's only been the last couple of generations they've unlocked it.
the AMD has, yeah.
Yeah, no, Intel has.
Oh, the Intel. Oh,
Yeah,
Intel's have they unlocked it for consumer now?
yeah.
Okay, yeah. Because I remember when I was building out my Windows server, I made sure I got an AMD CPU because I didn't want to buy enterprise hardware, but
Yeah.
I wanted ECC RAM.
In certain situations, particularly kernel down files, we get what's called the SM BIOS, which is like the when you go into your BIOS and you see things, well, that has to get presented to the operating system. So
Yeah.
SM BIOS is simple management BIOS, basic input output system. It's like a database of what the hardware is. So it tells you, this is my PCI device and stuff like that. The easiest way to explain it is if you go into device manager and you go view by connections and you see that tree.
Yeah.
Well, that's what it is. It's literally that tree in raw data form. Anyway, in there is the RAM, right? It says this RAM is in this RAM stick slot. This RAM stick slot is associated with this address range, blah, blah, blah. And then, other PCI device hardware is around it, blah, blah, blah. But what we have in there is actually the batch of the memory. And so we actually look at batch numbers and say, hey, particularly for Surface, for internal, we go, was there what do you call it, anomaly with that batch of RAM? Was it a bad batch? Because what tends to happen is the silicon, that wafer batch is just wrong, right? So anybody who came from that wafer is wrong. And we can tell by the numbers that it came from that wafer. And we go, yeah, it was just a bad batch. Rather than taking a step back and go, oh, we got a big issue here with supply chain. You go, no, we can actually isolate this to one wafer that went through the plant.
Yeah.
And that really did some things. I know when we were doing Surface Table, remember the Surface Table, the big table?
The big one, yep.
I was the EE for that. We were looking at the hard drive rate. It was one of the things we constantly checked, like, are we getting good batches of hard drive? And just to check that statistically, is it within range of everybody else?
Right.
Things you worry about. This is things you have to worry about as an OEM. Am I getting good supply of parts? And yeah, the granularity is pretty good.
So we've kind of been dancing around like this whole idea of like what is debugging at scale.
Yeah.
So let me just ask you, Andrew, like when we talk about debugging at scale, what are you talking about?
So everybody who's opted into it sends Microsoft telemetry on those 4 pillars: use mode crash, use mode hang, kernel mode crash, kernel mode hang, and we try to send the smallest amount possible. It's less than 64K, so it's quite small. And we try to make a signature of what happened without having to incur a cost of uploading a huge amount of data. And actually, we only have to upload about 0.1% of people's reports to be sure, so, statistically. And then what we try to do is we go, all right, this issue happened how many times? And then the way the Bang Analyzer looks at the world is timeless. And so when we're making a blame, so we may say this is a crash that's caused from an access violation. You'll have invalid pointer underscore. It'll be a read or write or an execute, because there's 3 types of AV. And then the error code is always going to be series 000005, which is the code for access violation. And then underscore the name of the, say, notepad, for example, and then bang, and then the function. It might be open printer, right? And so the idea is that this style of issue, a read type programming error, is happening in this function. And that's the granularity. So there's no version numbers for the app, no versions for the OS. So what happens is as you roll out, you can go, yeah, it's still happening in this OS. Or opposite's really true. We release the app, and then bam, it started. And then we see a certain version number happen, and then they fix it, and then you see that number disappear in the world. And then from a compatibility point of view, you actually have the opposite. And this is where the Windows side of my job comes in, is where you see the OS regress, and then where the application version number stays as a constant. And so you're checking, like, if you see OS regression, you go fix the OS rather than blaming the app, and then vice versa. If it's app regression, you blame the app, not the OS. There's a whole lot of debate around cause and effect. And a good example is maybe create file. So if you call into create file and give it a bogus string, right, some rubbish text for the file name, it's not create file's fault for using that string, because you have something bad, right? But what happens if you pass it null? Should it have a check for null? Right? It's like, is it still create file's fault even though it didn't have a null check? And then you take a step back. That's kind of obvious that you probably should blame the caller. So then what happens if it's CLR doing the exact same thing, right? And you end up with an IO file exception, right? Well, is it file exceptions for throwing? Probably not. It's probably the caller But what happens if that file thing is part of the assembly load code, and it's an internal exception?
So it's a complicated question of figuring out
And
who do you blame, right?
It's
That's
a
really
constant debate. It's a constant debate, and you're never right.
You're never right. But I think, you're trying to go and find, first of all, where to blame,
Yeah.
right? So where, like, what code is responsible for the blame, and then ultimately you want to try to get that to the people that can fix it.
Yeah, it's to the person who has the most probable chance of affecting change.
Which is interesting because sometimes the person who can fix the problem is not the person who wrote the code that's to blame.
Yeah.
Especially, like you mentioned, with compatibility, where there's a new version of Windows, and Raymond Chen has written this a lot, where maybe there's some buggy code, and there's a new version of Windows, and all of a sudden that buggy code in that app is crashing. Now, whose fault is it?
Technically, the OS was right in the first place because that was the contract.
That was the contract.
Doesn't
right?
mean Microsoft's off the hook.
So who fixes it? Well, not the buggy code. Sometimes it's Windows.
It's
right?
also the ability to get to that person.
Yeah,
Can you even
you can't recompile? Yeah. Sometimes, right? Yeah. Especially older code, and this was true for a long time, especially older versions of Windows. It'd be like, yeah, we have this line of business app, and we paid somebody to write it, and it's gone, and we're not going to upgrade Windows unless it works.
Well, even if they could, it's just it's been working for mine.
Yeah, it's been working, right?
And
why incur risk of doing some new version? Yeah,
it's interesting in the support world. You see a lot more. It's not Microsoft's fault. It's actually someone else who's actually injected something into the process that you didn't know about. Where it be a virus or antivirus, wherever it is, someone trying to enhance the operating system, and it just puts it into this unsupported realm. So then you end up with a triangle. It's like you got the customer, Microsoft, and the third party.
Yep.
And it gets even harder to debate. What's the best way forward.
Well, and that's a really common source of problems is code that's injected into other processes. I hear Bruce Dawson from the Chrome engineering team complain about this all the time when people think that they know what they're doing and they have drivers that have some code executing in your process. It's very common for graphics drivers, for example. We had an incompatibility in WinDbg Next for a while in the early days where there was some code, and I want to say, I don't want to blame a specific OEM. We'll say it was a mouse driver that was doing some special things. And so that code would get loaded into the process, and it would load debug help, which is one of the components of the Windows debugger platform. But the problem is it would load the wrong debug help.
Yeah.
Right. And so these sorts of problems are like everywhere, where it's sometimes it's not even obvious. Like, is there somebody to blame? Well, you do the best you can to find the blame, but from a debugging at scale point of view, you want to find the person who can fix the problem.
Yeah. And the other side of the debugging at scale is just the scale of it.
Yeah.
Our average is 2.8 seconds.
Now, 2.8 seconds to analyze a crash dump.
Unzip.
Load
the symbols. Run bang analyze, which does a lot of things, by the way, and then shut down.
Yeah, all in 2.8 seconds. Why? So
actually, it's down to 2.2.
Let me ask you a leading question.
How?
Why is no? Let me first start with why. Why is it so important that you're so fast? You're doing it in 2.8 seconds.
Pure compute.
Yeah.
Right.
What's the volume? Free. You're seeing huge volume.
Yeah, it's in the millions.
Millions. Yeah.
We run like 20 debuggers per server at the same time, right? And it's there's a lot of privacy things, so we run servers in burst on GDPR and all those other things in the right market. It's pure dollars, right?
Trying to get as many crash dumps analyzed with as little cost as possible.
You can probably guess in your head how much a server costs that has 20 debuggers worth of compute available to it to run for a year. It's not a cheap license.
Not cheap, no.
And there's not one of them, right? There's I mean, purely from a redundancy point of view, there has to be multiple per geo region, blah blah blah, right? And so it factors out to a pretty big bill. And so every millisecond counts. We were focusing on seconds. When I joined the team, one of the big things I did over the last 8 years, or something. Actually, it was the Monday of Thanksgiving 2017 is the week I started this because I decided to play that week. I wrote the kernel mode hang engine. And the kernel mode hang engine is an entire operating system. It has to read the entire OS and actually build up the entire OS in its brain. The scheduler, the processes, the threads, the virtual memory management, everything. The storage, networking, graphics, you name it. It's built in there to understand what the OS should look like for every version of Windows back to Vista. And that also we still get Xbox 360 traffic, which is NT4. And so it's a lot of diversity, and so its brain had to come up. And then when we first started it, it took 90 minutes to analyze a dump file.
90 minutes,
which is pretty good because you're analyzing 10,000 threads, loading a buttload of symbols,
all
that stuff, right? Then I got down to 30 minutes, which I was
Mm-hmm.
quite proud. And then I got it down to 30 seconds.
Mm-hmm.
And so hang analysis, a full box hang analysis, I think is currently 32 seconds average,
Wow.
which is it's doing a lot. I think we hydrate something like 60,000 concepts into our object database and into our namespace. And I can announce it. We're going to announce this actually. We're going to actually ship our thing. It's called Debug Analysis, the API. So there's Debug Client, which is the legacy stuff, and that's kind of like, as far as I'm concerned, kind of like the kernel version of the debugger. And Debug Analysis sits way up top at a very usable. It's all C# based invoked, much easier to interact with. And we'll release that by the end of this year with the debugger, and you'll be able to play with it, and you'll see a whole slew of new commands turn up in the debugger because
So
of
this
that.
is an analysis layer that sits on top of the raw iDebug client
Actually, it now
interface.
sits on top of target model.
Oh, it sits on top of
The
target
target
model.
model is so clean and so fast. It actually, debug client just actually calls down the target anyway. So we actually get it out of the way and go straight to the bottom for speed reasons.
Yeah. I mean, I know when I left the team, before I left the team, one of my goals when I was the lead was we wanted to move to be more modularized, so we could do those sorts of things, right? So it's good to see that those sorts of things are happening.
The other thing we do, which is a bit out of the box, is if you're in a user mode situation where Windows error reporting notices it's a hang, let's say that Notepad hangs and it's trying to you'll talk to the printer, right? Well, it'll be talking to the spooler, and so it'll get a dump file of Notepad, but it also will get a dump file of spooler, and then it might be talking to something else like an SVC host or something. Windows error reporting will capture all the dump files in the chain, in the web chain, and then we actually end up with multiple dump files in the zip. And so debug analysis opens all of them at the same time and merges them all together. And so you don't have to play this game of which dump file am I focused on. It actually hydrates it, makes it look like a kernel dump file that just happens to only have 3 processes in it. And that way you can walk from a code point of view through it and completely be blissfully unaware that there was actually multiple dump files.
That's really great. And you can have this analysis that doesn't really care what the physical representation is.
No.
Too often that's kind of a leaky abstraction because different types of kernel dumps have different types of memory, and sometimes there would be all this code that was like, okay, if I'm on this type of kernel dump, I know to ask in this way, and if I'm on this type of kernel dump, I ask in this other way.
Yeah, we have the data accuracy is actually probably 60-70% of my role is to get data out correct. What's the actual process name? Because you get mistakes, you get truncation. Sometimes, some reason it's in lowercase rather than mixed case, whatever. And you think about that for every data point you can think of. I spend most of my time on data integrity, actually more than analysis, because analysis we kind of more federate back to the team who owns the code. But yeah, the thing about going down, there's actually more than way down, right? You can ask the same question multiple times. And so you can get a process name from here and here and here and here. Well, guess what? Performance matters. So we actually track the cost of every single one down to the nanosecond and use the one that's the fastest.
Yeah.
And it matters. Like if you're doing it on every single dump file to get the process name, guess what? 3 milliseconds versus 2 milliseconds adds up over a year.
Yeah.
And so every single data point we get, we actually have clocked. And we were mainly at the millisecond rate, but now we have to do microseconds for all of our calculations because we're actually, the target model and everything is nearly every call is sub-millisecond. So we have to measure everything now in microseconds. Actually, we just do nanoseconds, but we had to go sub-millisecond because we weren't seeing the numbers anymore. So yeah, it's an interesting level of detail. And I harassed you over the years a huge amount about make the symbol performance better, make accessing this part of the dump file faster. And the target model answered a lot of those questions. They got a lot of the legacy code that was there for really good reasons back in the 90s and the early 2000s. It got that out of the way and let you go to the high-speed stuff. I mean, symbols is the other big thing that I spend a lot of time.
Yeah,
we're the co-authors of SimServe. So yeah, well, that's we've done a lot of optimization in there.
Yeah.
Lots of speed optimizations, just accessing files faster.
Symbols has always been a really hard problem, and I think part of it is, like you say, some of this code was built on top of assumptions that are 20 years old, 30 years old, some of them, and the symbols is no different.
There was only 1 or 2 CPUs.
There were only 1 or 2 CPUs. Symbols were, I guess they were still large relative to network size.
Yeah.
You didn't have symbol servers, it was, in the early days. And now it's like, symbol files can be absolutely enormous.
Yeah, bigger than 4 gig. Yeah.
Like Chrome.
Yeah. And every AAA game.
Every AAA game, because of the way you link and, if you have a big monolithic binary,
it's way more efficient.
It's more efficient in some ways.
So if you've got a 100 gigabyte COD download. Well, the XE in that's
Yeah.
probably 20, 30 gig. And guess what? The PDB is 2 to 3 times that. So,
Yeah.
um, yeah.
A lot of things that like were assumptions when some of the code was originally written, we'd be like, oh, well, we can do a linear search on this thing.
Yeah.
And all the times that Andrew would be like, yeah, so you do a linear search and this used to be a max of 100. Now it's a million or whatever, right? And now if you have some stacked linear searches, all of a sudden it's then squared. And we're like, okay, so now we have to go and do logarithmic searches and stuff like that.
There's some very interesting artifacts of this like perpetual world of Azure.
Mm-hmm.
Servers can be up for 2, 3, 4 years.
Sure.
And they're hot patched, which means their module list and process list gets over the years.
Sure.
And they're completely dormant and has no performance problem day to day. But when you look at the debugger, you're seeing the history in it. And so you get, 100,000 processes. Oh, yeah, a million modules. And yeah,
Sure.
as you say, searches actually really matter. We've done lots of optimizations, very micro ones too. Like we're shaving off 1%. But
if it's in an inner loop, that saves money.
Yeah.
So it's a hard problem to solve though, just in general. Like how do you, match all of the needs of accessing symbols to work for, scale analysis as well as, users, right? You mentioned something about how if there's a source of information that's from 3 different places, you're just going to pick the fastest one.
No, the most accurate first. Has to be
accurate first, sure.
And then fastest.
There's many cases, I'm working on my own debugger for educational purposes to teach you how debuggers work. And you just hit so many things, and I've talked about some of these, where there's 3 different sources of information. Which one do you show people, right? You could check all of them. Well, you don't want to do that in scale, in a scale analysis type of world. But sometimes they're different, and sometimes it matters. Yeah, it's weird.
The origin of data actually is something that we talk about. It's like, should we be tagging where this data point came from?
Yeah, and I talk about this for years. This is something where, and I think I had a tweet recently where I said, really every time something that's an analysis, like something that's in a debug engine, if I was going to write everything from scratch, everything should be tagged as why is this?
Yeah.
Like, where did this data come from? Because sometimes it's based on heuristics. Sometimes it's based on data that, could be fallible, right? A great example that, you and I have talked about many times is when you're filling in gaps of a crash num where we're not capturing the full memory of an executable image. Well, that executable image can be downloaded from the symbol server to allow analysis and pretend like that memory is there. The only problem is when that doesn't work, when the memory has been changed for some reason, and then you have an analysis where the debugger is essentially lying to you.
It's even worse than that. You get the situation where the symbol server doesn't match the truth.
The symbol server doesn't match the truth. That's also a problem.
And that's, you can't detect it. It's an undetectable thing at the client.
Yeah.
And so even just the trust of data's origin comes into play.
Yeah.
And we've wasted many a cycle, with this type of thing where you just thought you had X was the truth, and in the end it wasn't.
Yeah.
The big thing we learned in debug analysis was to tell the difference between 0 and null. And so every single one of it's all COM based. It's still a iDebug client style, but it's all COM. So it's like iDebug analysis, something like process and thread and frame. We use sFalse a lot, and it's a very rare return code for H results. Normally you return error. And so what we do is when the source of truth, when the data comes back as a source of truth, it comes back as SOK. If it comes back as a default, it comes back as sFalse. You go, well, why don't you throw an error? Well, it's not an error. We don't know what the answer is. It's a successful failure, right? It's not like, oh, we ran out of memory, something's corrupted, blah, blah, blah. We actually are in an error state. And when it comes to C#, if we had sent that back as whatever e-fail, guess what? You now have exceptions flying around left, right, and center in a C# application because it increases it up to exception. Its model of projection of errors is exception rather than error code. And so we use sFalse when you do things. And it's really good for things like you go, get PID. I can just go equals SOK because I know that the value came back. I don't have to go, and PID doesn't equal 0, right? Because internally it has some logic things that if it can't read it, it's a sFalse. But if it's an invalid value, we know it's defaulted. We also will use it sFalse. And that makes the code really clean. And so code velocity is really important when it comes to debugger, as in the readability of it and the efficiency of coding it. I've written probably about 700,000 lines in the last 7 years. And it's only because everything's clean. right? I never get tripped over it. And the debugger team's done a really good job of making an API that's clean and you can always trust the flow. Everything's single threaded, which is fantastic from a logic point of view. But yeah, the debugger, his entire role is no, don't lie to me.
Yeah.
Right? Tell me the truth, and then hopefully in the future will evolve to give us the attestation of its origin as well at the same time.
One of the leads I worked for before I was the lead for the debugger team was Jordy, and the thing that he always was, he was adamant about the debugger should never, ever, ever lie.
Yeah.
And sometimes that means doing some weird things where, version numbers is something that's come up recently where if you don't want to lie about the version number of a module,
then don't ask.
Well, then don't ask. It's true. Yeah. But you'll end up with an answer like, we'll give you the answer. There's 5 different versions for this module, and that's gotten more complicated as the Windows build system and release system and everything has gotten more complicated. But if you say, like, we're not going to lie to you, sometimes we're not going to lie to you, but we're going to give you a complicated answer that you really need to know how to understand.
Yeah.
But it's hard.
It is really hard. Jordy really is one of my heroes, I guess, for making me think about data. He poses this question in open-ended situations. If you had infinite compute and infinite storage, what would you do? Because technically, you could get every dump file and read out every single byte and represent the entire VA space of every process in big data.
Yeah.
No, obviously, it's a privacy nightmare. But in theory, what would you then do with that?
Right, because you can start with that perspective and then think about, okay, cool, that's what we would do. How do we solve this?
Well, what would I use it for, right?
Yeah, right.
And then you pare it back. And
say, how do I solve that?
And then you go things like, one of the ones that's kind of obvious is like, this is standard modules loaded in a DLL. Well, guess what? Normally when it's running fine, this is probably you need baselines, but if it's running fine, this is the 50 in it. Well, why do I have 52 in the crash case? Isn't it anomalous that these 2 extra ones have turned up and all of a sudden we're started to crash? And then you can look at what version numbers they are and stuff like that. And where do they come from? And then you start going, well, do we need the certificate information in big data? Because anybody can write common.dll. Like who owns common.dll or shared.dll?
Sure,
right? So then you need to roll back to certificates and stuff like that. But you can ask some very interesting questions if you take that ethos and take a step back and go like, if I have everything, don't worry about the compute to put it into big data, don't worry about the storage in big data. What am I actually going to do? Some really interesting projects have come out of that, which have now materialized.
Yeah.
Like a good example was that the memory stick serial number. Right? Just pull it out. We can afford the cost of it, and then we can work out whether there's batch errors.
Right.
Yeah. I mean, when it comes to big data, I track, obviously, the ecosystem. It's relatively flat. I mean, the same style of programming faults happen generically. I looked at the numbers this morning, and they actually have moved a bit. So access violation, which is when you access memory, used to be running at 52% for ages, and it's down to 40%. And then there's a side one called FileFast, which is C00409. That always runs at about 15%, and it's down to 10. And so we've gone from roughly 75 to 50, and it's like, that's because everything's more stable. Now, we fix the bugs.
It's interesting that you're looking at some of these statistics.
So Hangs has replaced it.
Hangs has replaced it, right? That's why things don't crash anymore now that Hangs. Have you looked at any statistics around like different languages? Of course, C# and C++ have both been around for a long time. Now that we're starting to see some Rust in Windows code, are we looking at any statistics around is Rust code more stable?
We know it's Rust. We can tell what language it is, but we haven't really seen Rust as scale yet that shows it statistically where I can.
You don't have statistically relevant information.
I looked at CLR. CLR is running at under 1%, but about I don't know what the CLR. I actually don't know what CLR usage is, but it wouldn't surprise me if it's around roughly the same area.
Yeah,
like 1% of apps are C#. So I mean, from a language point of view, actually, it doesn't actually matter in the end. When it comes to me, I'm actually down at assembler level. Actually, sometimes I'm down at microcode level because it's just, I mean, Rust turns into a C++ compile in the end, and then eventually turns into Link. It just happens to have all this, goo around it to solidify the way it works. And so in the end, it comes down to assembler. And so I actually am more interested in certain assembler blocks being consistent and problematic, whether these optimizations done at the linker level are actually causing the problem. But yeah, Java and all the ones that make native compiles, to me, actually, I don't spend too much time worrying about the language.
Well, I'm just curious if that's going to be, interesting, evidence supporting or not supporting moving more things towards Rust.
I think Rust is a great idea. I think you're going to see a class issues go from critical, like a crash, into framework, and it's going to be handled gracefully within itself.
Yeah.
And that's what I think some of the crash curve is, and the reduction of it is there's more and more frameworks capturing faults, and it's like instead of being critical and crashing, it's capture it and continue on.
Yeah.
And because it's very async nature of the world, because the world's become very irregular, non-deterministic.
Non-deterministic, sure. Yeah.
And so you have to code in a much more restrictive and reactive way.
Mm-hmm.
And so a lot of these frameworks are capturing the error and then just not showing you that panel in the application or whatever it is.
Yeah.
So it's hard to tell. I mean, I'm much more down because don't forget, for 99.9% of stuff I look at, I don't have symbols.
Sure.
It's all third-party code and stuff that we're analyzing. Yeah. And so all I have is the assembler.
Yeah.
Right. I can tell from some things that based on linkers and stuff. It's probably Rust, probably C++, whatever their origin is, why the PE header is written, but in general, I don't have the opportunity to actually be that lucky to actually see the source code. We don't do anything with source code. If everything's analyzed without source code, of course.
Yeah.
We don't have the time to look up source code.
Sure. Just thinking about sort of the analysis of scale that you're doing, I'm really excited to see how some AI technology is going to affect some of this analysis, although it's really hard to imagine how something like a large language model, which is really expensive to run, how we'll be able to use some of these things, and maybe we just won't be able to at scale for some long time unless it's at a sample level.
I've looked into this already. The problem with the language models is they can't deal with the complexity of programs yet. Mm-hmm. And so the idea is that you go, okay, we know this line of code's got a fault. Let's go, GitHub's a good example of their Copilot. They know what a good program looks like, right? The basic design patterns. And does this line of code not have the design patterns that everybody else is using? But just because you go, hey, let's use create file. Someone passed in a null. Yeah. I should be able to go if equals null, returned, you're a stupid idiot, right? It doesn't mean that the caller won't crash still. Yeah. They might expect a positive result always. And so when the LMVM looks at these things, it has to look into the context of the caller as well. And then that explodes the possibilities of what it could be. And they're not there yet. They can't afford, they can't do that compute yet. But I'm watching it. We'll watch it, and then Microsoft will definitely try to make it a product as soon as it becomes available, as far as we're concerned about what's possible.
Yeah.
I know Facebook has a thing they brought out maybe 3 years ago that actually does achieve this, but I don't think they did it through AI. I think they actually did it through a different system. I think they had more of an expert system to do it.
Yeah. Although I talked with somebody recently who works at Facebook, and I don't know what it's called, but I know that they've been experimenting with AI-driven, large language model-driven analysis of crashes, which I think is a really interesting thing to.
So we do that. So we have done AI where we've gone, look, because Banglize is an expert system, a massive expert system, with 30 years of expertise programmed into it. I've written an equivalent of Banglize in AI that just does cognitive recognition, and basically I crackle the function names into words. Like wait for multiple objects becomes wait space for space multiple space objects, because you just use camel case splitting. And then as a human language, it does a really good job of understanding intent, because the word wait and event and exception and raise turn up. And I got 99.7% accuracy getting the same result, choosing the same thread, choosing the same frame. I got an AI to do the same thing. Now, obviously, we don't use it because of money, right? It could achieve the same goal, but I can do it cheaper as an expert system. I can do it in milliseconds versus in a couple of seconds of AI compute.
Sure.
But yeah, it's 100% plausible. We are there from hey, out of all the threads and the situation you're in, what would you choose? And yeah, 100%. And we'll probably use that as we do more and more Linux.
Yeah.
Because we don't want to repeat 30 years of coding of Windows.
Right. It took a long time to build up a set of extensions and knowledge and expertise to build into that Bang Analyze.
There's been between 1 and 3 developers on it nonstop for 30 years.
Yeah.
Which is, and they're nearly always principal level too, so very high level. So we're cranking out a lot of insights. It's probably had 50 to 100,000 check-ins over those 30 years.
Sure.
Yeah. It's a big code base.
Is there anything you're excited for? I mean, obviously, might be some things you can't talk about, but are you excited in terms of like technology you're seeing coming?
I love tinted projects. No, I think this synchronous world is very interesting. I'm interested to see how this much more dynamic world is going to affect the way we look at reliability. Um, People are actually thinking about it more, so I'm excited to see quality get better and better and better.
Mm-hmm.
We're actually at the point when certain metrics where we don't need to invest in it anymore because it's actually a self-healing situation, and we actually can now spend time on evolving technologies. Like kind of like blue screens, the rate is so low, it's solved, right? Nearly always it's down to some hardware fault these days.
Mm-hmm.
I looked at the numbers. The number one thing is a power transition in hardware, and number two is a USB device failing. These are physical hardware things because you've got cheap, nasty hardware with bad drivers or bad. And there's nothing that Microsoft can do to fix that, right? It's just the artifact of having a diverse ecosystem with, unfortunately, bad quality components in it. I mean, I personally have not had a blue screen on my home box for 2 years.
Yeah,
Right.
which is crazy, being from the world of,
Yeah.
you started earlier than me, but even like when I started like with Vista, it would be like, we would not get through the day without a blue screen
I don't remember.
when we were working on it.
Yeah, I mean,
right?
definitely that's what being Xcode. I mean, as soon as you look at retail, it's so much more solid. Sure,
Yeah,
as
yeah,
an
yeah.
insider, you're going to get it because we're trying really hard and
Yeah.
we react to it and it's fixed. But
Well, even as an insider, though, I feel like there's a huge difference between what we experienced when I was an intern on Vista versus like, Win 7 was better, Win 10 was better, I guess I didn't really do much with Win 11, but like, and I think part of that is due to the fact that you can quickly find the problems and fix them while it's still in development, so that if I'm running that internal build of Windows, it's not the crashing every day experience that it was for Vista.
We catch a lot of issues as they we call RI. So as the branching goes up to main, we catch a lot as it goes up through the tree, and so it doesn't escape, as we call it. So that's been really good. I think long term, I'm interested to see how MPUs and all those affect really SoC. So system on a chip offload, how that evolves the industry. The idea of a CPU doing all the work is in the past. Like everybody's MPU is a good example of that, right? You couldn't do neural processing in a CPU; it's not performant. Make custom silicon. GPU is another example in the past. Like you can't do graphics in a CPU, put it into a GPU, right? And I think we're going to see more and more of those things. There's a lot to be said about having a chip that sits there dormant when your laptop's turning off, just pinging the cellular towers and doing whatever it needs to do. Don't wake the CPU for that. Don't wake anything else. Just have this tiny little thing on the edge that is keeping your location up to date. So if your device is stolen or whatever you're trying to track it, it's calling home, right? And so you don't need the CPU to turn on for that, right? So there's all this SoC offload, and it's going to push the debugger to limits because what data do you collect? Just because of an application notices a failure, well, capturing memory from an application does not help you anymore, right? Because it's all offloaded. And I think we'll see this in server before. Well, it's a bit 50-50. I mean, phones is already at its point, but in the cloud we'll see this a lot as it's a power efficiency and sustainability story thing. And then in desktops or in laptops, particularly things that are more portable, we'll see this SoC offload a lot. It's interesting to see ARM grow. That's an interesting thing. I actually spent my from about 95 to 2000 working on DEC Alpha. I actually spent more time coding on DEC Alpha than Intel because all of the newspaper stuff was DEC Alpha based because it was super fast. And that was basically the same as ARM. It's got the same RISC instruction, very low number of instructions. And so it's good to see that come back from a nostalgia point of view. I'm enjoying watching 32-bit fade out.
Yeah, that's true. 32-bit is starting to go away now.
Yeah,
or is there? I think on like server that hasn't been 32-bit in a while.
No, it's been
on
Windows
11 client. There's no 32-bit anymore, right?
Yeah, WoW's 32-bit support. There's no 32-bit OS,
but there's still 32-bit WoW. So you run 30-bit programs in a 64-bit OS. That's probably going to last for a while. There's a lot of 32-bit.
But the ARM ARMization of the world. Well, you don't run ARM on ARM64, so it's forcing native ARM.
Yeah, so you have native ARM64 stuff. Although we'll probably still run 32-bit x86 on ARM64.
But that's right. But from an emulation point of view.
Emulation, sure. That's the path to compatibility long term, and you can
emulation. And then there'll be. I wouldn't be surprised to see a new chipset turn up. Quite frankly, I think there's been so much realized worth in the way that a new CPU has turned up. I can see another player somehow turning up and evolving it again. And I'm not talking next 5 years, but in the next 10 years, 20 years, I can see another. I mean, quantum's going to turn up at some point.
Yeah, I know Microsoft announced that they want to build a quantum supercomputer in the next 10 years. We'll see what that turns into.
And then the VR AR revolution is going to cause a
That's
very
right.
interesting.
Entirely new hardware that you need, new debugging techniques you'll need, or well, already need for
Yeah.
debugging that stuff.
The big thing that I'm dealing with is this transition from crash to hang though. So
Yeah.
you go from this tiny little
Yeah.
emphatic thing to, okay, let's look at the entire world and work out what's wrong. And
Yeah, I mean, in some ways, crashes tend to be, I won't say simple,
yeah,
right?
simple.
But they are simple compared to hangs, because a lot of times your crashes, either it's right there on the top of the stack or it's a couple frames down, and really,
Or it's for a transport that is walk backable.
sure, right. I mean, the only time,
that is a big change. So crashes rarely happen at the place of the crash anymore. They are transported because of the asynchronous boundary.
right, they're
bundled
crashing and then it's being bucketed or
and then
bundled and moved
transported.
over. Yeah, yeah.
Yeah, because the exception handler is on the other side, on the outside.
Right, right,
And so
right.
it's
So
not.
something crashes, but it's not, yeah,
Yeah,
the physical cord.
all the major work I've done in that space has been transport based. So
Sure,
XAML
sure.
exceptions, Stow exceptions, C
Yeah.
sharps, blah, blah. So all these transport ones, that's a big thing
Yeah.
that changed.
I mean, the ones that are really hard there are the ones where you're, it's a crash because something is in a bad state, maybe some memory is in a bad state, and you have to ask the question or answer the question, why is it in a bad state? I don't know if that bug still exists, but for many years, there was a crash that would just occasionally show up in the crash collection code in Windows, which is really
I remember you talking about
fun.
that.
Yeah. And for a long time, we would look at it and we would say, yeah, like the memory is wrong. We know it's in a bad state. We don't know why it's corrupt.
Yeah.
Like clearly it's a bug in our code. I actually heard maybe the team figured this bug out, but anyway, it's like those are the hard ones, right? Where the memory is corrupt.
Memory corruption is always going to be the worst thing in the world.
You got to ask and answer the question of like, why is this corrupt?
Yeah.
Right?
And going full circle, that's Bitflips is part of that story.
Bitflips is part of it, yeah. But when you see patterns where you're like, this is consistent, then you're like, okay, there's a bug in the code, it's corrupting the memory, and we don't know why.
And that's where Rust has its power, and C# as
true,
well.
yeah.
It basically you don't see memory corruptions in those worlds.
Yeah, it's funny because I wrote a lot of C# when I was at Microsoft, and it's the types of bugs that you see are just totally different. The types of crashes, the types of bugs. When in the C++ world, a lot of the core debugger engine, it's all C++ and C, and you would see access violations, crashes of different sorts. You don't see those really in C#. Occasionally you do, right?
And it's usually
but it's a completely different.
It's
set
usually
of
when it's interrupting with C++.
That's true, right? Yeah, interrupt with C++. That's true.
I mean, I love C#.
I kind of miss that in a way. Not that I think it's better, but I enjoyed debugging some of those things. I was talking about this with Mario Heurix, and I like debugging those things, but I realize the world is a better place without crashes.
Yeah. But the problem is, in the absence of a crash, you may have unstable behavior.
That's true,
which is
right?
Way harder.
If you've got an exception being thrown in C# and it's getting swallowed, and maybe your system is in a weird, inconsistent state, but it's not crashing, is that better? Maybe not.
And it comes once again came in full circle. It comes down to the criticality of the app. Is it going to cause a live event?
Yeah.
Right. And sometimes it's better to be terminal and restart than have this lackadaisical, weird state.
And that can be very different based on like client applications versus server applications.
Yeah.
On a client application, if you're using WinDebug and WinDebug crashes and you lose all of your data, that's a problem. I would rather be in a slightly inconsistent state and be able to recover my data. Whereas in the server world, it's like container crashes. Blow up as fast as possible and
get
restart.
out of the way.
Yeah.
I think thinking about data and data centers, the biggest problem we're going to have in the debugging space going forward is data sovereignty. You can't run an AI model. I can't get a dump file and put anything from that dump file, as benign as you believe it is, into AI.
Yeah.
Because I can't disclose people's function names. I can't disclose people's exe names, their module names, let alone God knows what's in a message.
Right.
And so you can't. So debugging cannot evolve in this AI model until we work out a data sovereignty model where you can run maybe the model locally or in some secure environment that has a certain attestation to it. And that's I can't wait to see AI get to a point where it's mature enough from a data privacy point of view that it can then be leveraged in highly confidential situations.
And that's a problem that, you and I talked about it for many years of, we want to have high quality diagnostics, high quality, bugs fixed without sacrificing privacy.
Yeah, privacy number one.
It's, I'm sure there are still people that are distrustful of Microsoft in terms of privacy. But I look at how much work you and I personally, as well as the teams that we worked with,
Yeah.
we spent all this time trying to make sure that we could get the diagnostics we needed while not, having any information that could be considered, personally identifiable information or anything like that, respecting privacy as much as possible. And I think there's going to be a little bit of a learning experience in some of the AI world around people and how they treat customer data, how customers expect their data is treated.
Yeah, and it takes one mistake to lose that trust too, right, with a company.
Absolutely.
And I don't know, sure, you might have the best intentions, but a leak is a leak.
Yeah.
Right. You didn't understand ramifications. Now, in certain situations where the privacy of the data, sure, there's scope. Like, it's my application and I want help, fine. But when you're taking in data from someone else, it's a completely different story. But it's a fantastic place to be in. Like, you've seen me every week. We used to have a meeting about what's going on. Every single week, I'm doing something different, right? And I'm pushing you guys to give me what I need to respond to the latest, not crisis. We don't have crises, but everything's always crashing, so nothing's ever a crisis. So there's always something going wrong, so nothing's always going on. So which is great when you get to breathe, you get to take a step back and look at things holistically. But about learning, it's a great way to learn because you're constantly being fed with this new, I didn't know that this thing existed. Let's learn about it. Let's reverse engineer it. Let's work out how to analyze it.
Working anything diagnostics, I just feel like, you learn a lot of, low-level stuff and just breadth of knowledge of how stuff works. Because if you're helping figure out why things aren't working, you got to figure out how it works.
That's where chronology comes into it. Like TTD.
Sure.
The number of times TTD has saved me is uncountable. It's amazing. Chronology is the next probably bigger evolution. You've got AI for insights and probably the concept of chronology in the data where you can wind back time.
Right. And TTD is time travel debugging, which is capturing traces of program execution, which is built into WinDbg.
And that will move to a silicon level, I think, at some point. I think they'll.
For a long time we wanted that. Hopefully that'll be something.
They'll get the speed up.
Yeah. Well,
fun stuff.
For sure.
Yeah.
It's been great catching up with you, hearing a little bit about where you came from. Hopefully folks will find that interesting.
Yeah. It's great talking to you guys. We'll hopefully have something to announce about a new Channel 9 series going forward.
Yeah.
I'm trying to pitch it. It's a full debugging series, how to learn how to debug. So debugging
that would be great.
Debugging 101.
That'd be great.
So defrag tools and OM have the episodes. It's just the problem is it's mixed in there rather than having just in linear. So it'll be debugging for beginners.
It's a hard thing to teach, but it's worth trying.
But I might harass this guy and see if he can be on stage with me. But,
I'll be on stage whenever you want.
But hopefully we'll get that done, and then we can bring the love of debugging to more people.
To more people, that's right.
Yeah.
All right. Well, thanks, Andrew.
Thanks.
Fun talking to you. Hope everyone enjoyed this. See you next episode.